So, starting with some examples. Example 1 does say that we have 2 to the 3/4 power times a 2 to the 1/2 power. And if we were to look at our laws of exponents, I believe that's the first little property. If we're multiplying and we have like bases, what are we doing with those exponents? What are we doing with those exponents? You add them. So when I look at this, I just heard you say we're going to add the exponents. But now when I add and I have fractions, what do we need to make sure when we add fractions? Adding and subtracting has to have what? Yeah, that same denominator, common denominator. So when I look at 2 to the 3/4 times 2 to the 1/2, we're going to add those exponents. I need a common denominator. 4 would be a good one. 2 changes to 4 by multiplying by 2. What I do to the bottom, you do to the top. So we have 2/4 and 3/4 added together to give me 2 to the, how many fourths? 3/4 plus 2/4 is 5/4. And that would be my answer. So multiplying and having like bases, remember the 2 is the base, the 2 is the base, we can add the exponents. And yes, we get 2 to the 5/4 power. Example 2. I have a 3 fraction bar, 3 to the 1/4. What kind of math is going on in a fraction? Division. So again, if I take a peek and try to find a fraction or a dividing monomials, here's my dividing monomials. When I have like bases, what are we doing with our exponents? Subtracting. And I'm also going to tell you that subtracting will happen, and I would like it to be where the bigger exponent is, because then you have less chances of dealing with negative exponents. So I'm going to just add a little extra. Subtract where the bigger exponent is. And I'm going to abbreviate because I'm kind of running out of space there. So subtract where the bigger exponent is. Well, I'm going to say, what is the exponent on this 3? I don't even see an exponent. Do you? What can you always put in front of something, underneath something? 1. So that's the same thing that applies with my exponents. I can always stick a 1 out there. Well, which one's bigger, the 1 or the 1/4? 1. So we're going to subtract up top. So 1 minus 1/4. And then that means that this isn't really there. And hopefully you don't have to think about, you do have to think about common denominators, but hopefully you don't have to punch that in. We should know that 1 minus 1/4 leaves me how many fourths? 3. Very good. Again, if you're not so good with fractions, if you don't want to go through the common denominator conversions, you know that calculators punch in, you can punch in calculators, fractions, right? Yeah. Okay? And that would be our answer there. Questions? Again, making sure that yes, you have to have like bases in order to use these rules of adding or subtracting. If you're dividing, you're going smaller, makes sense we would subtract. Multiplying, you're going bigger, makes sense we would add. Going on. Ooh, I like number 3. If I think of number 3 as like an order of operations, what would we do first? if I think of number 3, like an order of operations, what would we do first? Parentheses. But now if I look at what's in parentheses, I can't really say that I can subtract exponents because I have a 20 to the 1/2 power and a 5 to the 1/2 power. In order to use these laws, we have to have like bases. Like bases in order to use these laws. So then I'm going to say, well, what else do we know about these rational exponents? So if I take and say, okay, what do we know about a 1/2 power? What is it really if we think about radicals? A 1/2 is really a what? A 2, and what do we call that 2 with the radical? What do we call a 2 with a radical? What do we call that thing if it has a 2? It's a square root. So if I were to say I have a square root divided by a square root, if we look on the back of our little cheat sheets, there's a little quotient property. It says if I have the nth root of A divided by the nth root of B, I can write it as one big radical of an nth root. So if you look over here, this kind of helps us see it a little better. They have a 4th root of 162 over a 4th root of 2. They wrote it as one big 4th root of 162 divided by 2, and then they reduced it. Can we do the same thing here, but use it as a big square root? Yes, we can. So we're going to take this and write it as one big square root. I don't really need the 2. If you have to have the 2 there to help you visualize I need 2 of the same factor, then do it. But you don't have to write the 2, but it's 20 divided by 5. I still have, and I didn't write it, I'm sorry, we should. We still have the cubed outside. Don't forget that because that is part of our problem. And if I think of 20 divided by 5, can I do the math? Yeah. What's 20 divided by 5? 4. Square root of 4 is really what number? 2. So this right here breaks down to be a 2. I still have a cubed here. And 2 cubed is really what number? 2 times 2 times 2. 8? Is that what I heard? Yes. Very good. All right, so let's look at this. You told me to work in the parentheses first because that's order of operations, right? We couldn't really subtract exponents because I didn't have like bases, meaning I didn't have a 20 and a 20 or a 5 and a 5 as my bases. So then I said, what else can we do? Rational exponents are radicals. Radicals are rational exponents. So sometimes we're going to change it so that we can work it down. It didn't work itself down when I was dealing with these rational exponents. But when we put it into radical form, we had a square root over a square root. We had our little property here that says, if I have like square roots, I can write it as one big square root. So we wrote it as one big square root. Again, if you need to put the 2 there, you can. It's not needed on a square root. 20 divided by 5 is 4. Square root of 4 is 2. We still have that cubed, so we still had to say 2 cubed, which really is 8. We good there? So sometimes we're going to go back and forth in between what do we know. Oh, well, sometimes we're going to use those laws of exponents. Sometimes we might have to go from rational exponents to radicals to work it out to get that simplified answer. And that's where some of us might have some difficulty because it's not all one fits all kind of solve it down problem. They're all a little bit different. Okay? All right, on to number 4. Yes. Question or bless you? Bless you. I think it was. All right, on to number 4. I have a 5 to the 1/3 times a 7 to the 1/4. And this is a quantity cubed. Again, if I look at that as a multiply and say, can I add those exponents? Are you going to say yes or no? No. Why not? Very good. If you look at this base, it's not the same as this base, is it? Okay? So, if I look at that and say, well, can I write them as radicals? I could. Let's go ahead and try that, because isn't that what we did over here? But notice this was a 1/2 and a 1/2, so I don't know if that's going to help us either. But if I look, a 1/3, that's going to be a cubed root, correct? And some of you say, well, where's the 1? Like over here, you might say, well, where's the 1 when we did the 1/2? It's really here. It's really here. It's just we didn't write it, because 1 doesn't really change anything, does it? Okay, so a 1/3 is really a cubed root. This 1/4 is really a 4th root. Does that help us any? Can I write it as one big 4th root or one big cubed root? No. So we did that step for no reason. The only way that we can simplify with radicals is if we have the same radical. And right here, I have a cubed root and a 4th root. They're not the same. So this doesn't really help me. So now I have to say, okay, is there something else we might try using a property? Okay? And if I were to say, okay, I don't care either side, I do have a power to a power, right? This is a power of 1/3. This is a power of 3. So that's really a power to a power. This is a power of 1/4. This is a power of 3. It's really a power to a power. So if we look on our little cheat sheet, which is kind of a bigger one on the front, we have powers of powers right here. There's one example. There's one example. If we look over, it says that we're going to multiply the exponents. Multiply the exponents. If you have a power to a power, multiplying my exponents. Says it on both of them. Okay? If I want to look on the back. Oh, here's a power of a power. Here's a power of a product. And again, you're multiplying or distributing the exponent. So we're going to do that. We're going to see if that helps us any. And it might not, but hopefully it does a little bit. So I'm going to go ahead and say distribute and multiply those exponents. So I really have a 5 to the 1/3 times 3. I really am going to distribute to that 7 and the 1/4 times 3. Power to a power, we distribute and multiply. Well, if I think about a 1/3, it's a fraction. I was always taught if one thing's a fraction, make the other thing be a fraction. Can't I stick a 1 under that 3? Yeah. Same over here, 1 under that 3. And then remember when you multiply fractions, it's top times top, bottom times bottom. So what happens with my 1/3 and the 3? If you multiply them, what do you get? 3 over 3, which is, right. So I really have a 5 to the 1 power. Do I need the 1? No. And then if I multiply my 7, 1/4 times 3 over 1, what do we get there? 7 to the top times top, bottom times bottom. 3/4. And then that's all we can do on that one. Does it look simplified? Not much. The only thing that simplified was my 1/3 and the 3. So sometimes it may not be, simplified down where it's just an answer of like we got last time, which was 8. But on this one, we tried our radical form. couldn't make it be one big radical, so we said, okay, what else could we try? And I kind of pushed you towards your cheat sheet. A power to a power, you multiply the exponents. When I multiply my exponents, yes, the 1/3 and the 3 cancel, leaving me with just 5. And my 1/4 to the 3 gives me 3/4. And that would be your answer. So like I said, this chapter, this section gets a little tricky as we keep going because there's not a one solution fits all problems, okay? Different laws to different problems. Sometimes we're going to go from rational to radicals, radicals to rational. We don't know what's going to work until we try it. All right, on to, there's a little bit of vocabulary I see on that sheet. So let's look at the vocabulary and put those in our notes. All right, it says something about conjugates. And they give us a little example, and they say an example of conjugates is 5 plus square root of 3 and a 5 minus square root of 3. Well, that looks kind of familiar. We've done a little bit with conjugates. We just didn't call them conjugates. Remember how you were given a 0 and you were to write the polynomial and it went into your parentheses opposite of what you saw? So we've kind of dealt with those. They're very similar. The only thing that differs is the sign in the middle to make conjugates. Conjugates are going to come into play when we do some dividing, okay? And you might have a binomial in the denominator, and for some reason, whoever invented these radicals, rational exponents, you can't have them in the denominator, okay? And likewise, if I had something like a 1, say, minus 2 to the 1/3 power, what would be its conjugate? Well, these are exactly the same. The only thing that differs is the sign. Yeah, so this would be a 1 what? Plus 2 to the 1/3 power. Those are conjugates as well. The only thing that differs, the plus and the minus and the plus. Bless you, bless you. They also have some, like radicals is what they talk about next. Like radicals come into play when we add or subtract. And in order for something to be like radicals, they have to have the same index. And the index is the root or radical. So the same index number and radicand, which is a number underneath. Index ties into the little number with the root or radical. The radicand is the number underneath the radical sign. And it's mainly for when we add or subtract. So then when we go to look at the next lines of work there, we have a 4th root of 10 plus a 7 4th root of 10. So when we talk about this index and radicand, the index is the 4, they're the same. The radicand is the number underneath, which is 10 and 10. So if they are like radicals, then we can go ahead and add. So I think about what's really in front of this 4th root of 10 could be a 1. So if I do add them together, how many 4th root of 10 do we really have if I have 1 plus 7? 8. If I look at the next one. Similar, but it's in rational exponents, which is still a radical. I have a 2 and an 8 to the 1/5 power. Again, this right here is similar to an index. This base is similar to the radicand. So then it has a 10 and it has an 8 to the 1/5 power. So if you see it in rational exponent form, you want to have the same base with the same power. This would be like the index. This is like your radicand. And then if I look at that, I can go ahead and add, and the only thing you add is the numbers out front. Or subtract the numbers out front, but this is an add. So how many 8 to the 1/5 do I have if 2 plus 10? 12. The next example say they're not alike, but I disagree. They're not alike in their original form. And why are they not alike in their original form? I do have a cubed root and a cubed root, but the radicand is a 2 and a 54. So how are they not alike? Yeah, the little number underneath known as that radicand. The radicands are different. But I'm going to say, we've had enough experience that we should know if a number is bigger, we might break it down and see if it fits. Okay? It could be in disguise. So these examples right here that yes, they were alike. Yes. Yes. This one is a no from the get-go, but there's always those exceptions to the rules, right? Yeah, there's always those little pigeonholes that sometimes people find to get out of being in trouble with the law. Oh yeah, we have those special cases in math where, again, one size doesn't fit all. So we have to try something else. Well, and if I look at it, I know that 2 doesn't break down. 2 is a prime number. So I'm going to say, let's try and break down that 54. Well, what are factors of 54? Factors of 54, class. Nobody knows any factors of 54? Think, odd or even? 27. Oh, I wouldn't even have chose 27, but 2 and 27, right? Factors of 27. Hello, factors of 27. 3 and 9, thank you. Factors of 9. All right, so if I look at this, I have a 3, a 3, a 3, and a 2. What does this cubed root out here mean again? If there's 3 of the same, you take one out. I'm hearing that. 1, 2, 3. A 3 is going to come out. What happens with this number if it doesn't have 3 of them? Very good. It stays underneath a cubed root. So I took a 3 out because there's 1, 2, 3 3s, and that's what a cubed root means. And then the 2 stays in. Well, we said no, they're not alike. We were wrong, right? They are alike. It's just they're in disguise. So sometimes you might have to break down the bigger one to see if it is truly a no or a yes, because this one actually does work out. And we can work it out to get a answer. And what would we get? What's really in front of this one? A 1, but it's 3 minus 1, which gives me how many cubed root of 2? What would be my answer? 2. So even though at the beginning form they were not alike, that 54, cubed root of 54 was in disguise because it did break down to be a cubed root of 2. So before you say yes, they're alike or no, they're not alike, actually break it down if you can, because you always want to work with simplest form. So if you can break something down, do so. And then yes, we did actually subtract and got our answer. So that one is also a yes. They are alike. All right, so a little bit of vocabulary to kind of keep in mind. There are 3 more examples that we're going to get to, and those are dealing with radicals instead of rational exponents. So like I said, we're going back and forth. Keep in mind as well, if you start with a radical, if you start with radicals, your answers are usually going to end in radicals. If you start with rational exponents, your answer probably is going to end in rational exponents. They might simplify altogether and just get a whole number, but keep in mind that paying attention to how your problem started, if it started in radicals, your answer is probably going to end in radicals for the most part. Okay, and so the next ones we're going to radicals, which are some more examples to tie into our 5-2 using our laws of exponents. All right, some more examples. And 5 says we have a 4th root of 27 times. Now, I know you're going to say they're not alike, so we can't do anything. Multiplying is different. All of these problems up here that we were talking about, these like radicals, tied into the add or subtract for the most part, okay? These were adding or subtracting. So when we talk about multiplying, multiplying is different. Again, we could try to break down our numbers, because I know one of these numbers is going to break down. Which one would break down? The 4th root of 27 or the 4th root of 3? Which one breaks down? Yeah, very good. So if I look at this and I say, oh, well, they're not alike, I can't multiply. That is not the truth. So if you look at your little cheat sheet on the back, here's a multiplying problem down here. Nth root of A, nth root of B, if they have the same nth root but different numbers underneath, you can multiply them and get an answer. Okay? Just like if I had an nth root of A divided by the nth root of B, you can divide them and get an answer. Okay? So multiplying and dividing, you just have to make sure that the radicals or the index number are the same. The numbers underneath, they're okay to be different if you're multiplying and dividing. If you're adding and subtracting, they have to be the same. A 4th root of 10 has to be with a 4th root of 10 if you're adding or subtracting. 8 to the 1/5 has to be the same as an 8 to the 1/5 if you're adding or subtracting. We had to do a little bit of changing here to make them be the same, but a cubed root of 2 has to be with another cubed root of 2 to add or subtract. Here, we can say, I'm going to write it as one big 4th root. But you also told me I could break down my 27. So if I were to say, let's break it down first, and then we'll write it as one big 4th root, either or, it doesn't really matter. But factors of 27, what do we have? 3 and 9. 9 is 3 and 3. I can't take a 3 out if it's a 4th root right now, can I? No, but if I write it as one big 4th root, and my 27 is really 3 times 3 times 3, and then I also add this 3 because it was both a 4th root, now can I take a 4 out? I need how many of the same factor? 4. I had 3 right here from 27. I have that other 3 that says we multiply it. 1, 2, 3, 4. A 3 comes out. 1, 2, 3, 4, which a 4th root, a 3 comes out. All right. On to 6. Questions? So technically we wrote it as one big fourth root. We broke down 27. We needed 4 3s to bring it out. We had them. All right, number 6. Cubed root of 250 divided by cubed root of 2. Similar to one of those first examples we did, right? I think so. Similar to this one right here, but it wasn't really in radicals to start out with, but we changed it so that we had a square root of 20 divided by a square root of 5, and we wrote it as one big square root. Can we do that with this one, but put it under a cubed root? Yeah? All right, let's do it. One big cubed root of 250 over 2. All under that one big cubed root. Is 250 divisible by 2? I think so. It's even. So what would we really have under there? Cubed root of, what is 250 divided by 2? Very good. 125. Is 125 a perfect cube number? Yes. What's our answer? 5. If you're not sure how she got that, think about there's 5 quarters and $1.25. 25 is 5 and 5. Again, if I think about this, I need how many of the same factor? I need how many? 1, 2, 3, and a 5 comes out. 1, 2, 3 5s, the 5 comes out because it's a cubed root. Do I have to show this work if I know the cubed root of 25 is 5? The answer is no. We should start being familiar with those perfect cubed numbers. Keyword should. Everybody's a little different with their math facts. All right. Similar to that first example in that first chunk. Oh, what about number 7? It only has one little cubed root. But remember how I said we always want simplest form of things, yes? If it's not a prime number underneath there, then we might try to break it down. If it's just one number, all of these examples probably would have had, directions of saying simplify. So if I look at this one, we're going to try and simplify. If it's not a prime number under there, we're going to break it down. Always simplest form if possible. So breaking it down, what goes into 104? What number do we want to use? Don't everybody speak at once. 2, 4, 6, 8, 3. What do we want to try? 2. Sounds good. So that would be 52. Breaking down 52. All right. 2 and 26. 2 and 13. I hear you saying 2s, so I'm going to do 2s. 13 doesn't break down, does it? No. So these are my factors. And again, I think about it. How many of the same do I need in order to take one out? 3. So what comes out? A 2. What stays in? A 3. Don't forget to leave it as a cubed root of 13. So for every 3 of the same factor, we can cross out 3 2s. A 2 comes out. Whatever doesn't come out stays underneath the cubed root. And that would be your answer. So again, breaking down our numbers, realizing what these index numbers truly mean. If it's a cubed root, we need 3 of something. If it's a 4th root, we need 4 of something. If it's a 5th root, 5 of something, and so on and so on. Okay? That is where the other classes stopped, so we're going to go ahead and stop there.